The speed of light sounds like a simple fact, a number memorized in school and repeated so often that it risks losing its significance. Yet this single value quietly governs the deepest structure of reality and defines what is possible in the universe. At first glance, it seems like just another impressive statistic, an almost absurdly fast velocity that only matters to physicists, astronomers, or science fiction writers. But the moment you begin to understand what this speed truly represents, it stops being a number and becomes a boundary. It is not merely how fast light happens to travel, it is a fundamental limit woven into the fabric of space and time themselves. Everything we experience, every event that can influence another, every cause that can lead to an effect, is constrained by this cosmic speed limit. Nothing with mass can cross it, nothing can outrun it, and nothing can bypass it without tearing apart the logical order of reality. This limit is not imposed by technology or engineering, but by the universe itself, and its consequences are so counterintuitive that they force us to abandon the way we naturally think about motion, distance, time, and even the present moment. When objects approach the speed of light, time itself begins to behave strangely, slowing down relative to those who remain behind, while space compresses in the direction of motion as though reality is folding in on itself to preserve this unbreakable rule. Events that appear simultaneous to one observer are no longer simultaneous to another, and the idea of a single universal now dissolves into something dependent on perspective and motion. These effects are not speculative or philosophical curiosities. They are measurable, tested, and confirmed facts that modern technology depends on every day. Navigation systems, particle accelerators, medical imaging, and space exploration all rely on the universe behaving exactly this way, even though it defies common sense. What makes the speed of light so extraordinary is that it applies equally to everyone, everywhere, regardless of how fast they are moving or in which direction they travel. Unlike sound, which depends on air, or waves in water that slow and speed up depending on conditions, light in a vacuum always moves at the same speed, no matter who measures it. This constancy is not an accident, but a clue, a sign that space and time are not separate, rigid backgrounds but flexible components of a single interconnected structure. The universe does not allow velocities to add in the way our everyday experience suggests, and when motion threatens to push beyond the cosmic limit, reality itself compensates by altering how time flows and how distances are measured. This is why the speed of light is not just about light. It governs all forms of causality, determining which events can influence one another and which are forever disconnected. It defines horizons beyond which information can never reach us, shaping what we can observe and what will remain permanently hidden. Entire regions of the universe exist beyond our ability to ever see or affect, not because of distance alone, but because the expansion of space combined with the finite speed of light places them outside our causal reach. Even within our own galaxy, this limit turns stars into isolated islands, separated by gulfs so vast that communication takes years or centuries, and travel within a human lifetime becomes nearly impossible. The speed of light, therefore, does more than constrain movement. It shapes the structure of the observable universe, determines the size of cosmic horizons, and sets the ultimate boundaries of exploration and knowledge. It also connects mass and energy in a profound way, revealing that matter itself is condensed energy locked into form, capable of being released with astonishing power when the conditions allow. This single constant links the smallest particles to the largest structures, from the decay of subatomic matter to the life cycles of stars and galaxies. For centuries, humanity assumed that time flowed uniformly, that space was absolute, and that distance meant the same thing to everyone. But the realization that the speed of light is finite shattered those assumptions completely. What emerged instead was a universe far stranger and more subtle than intuition ever suggested, one in which motion alters reality itself and limits are not obstacles but defining features. Understanding this speed is not about memorizing a value. It is about recognizing that the universe operates according to rules that are deeply unintuitive yet astonishingly precise, rules that challenge our instincts while revealing a deeper, more coherent order beneath the surface of everyday experience. For most of human history, the idea that light might take time to travel simply did not exist, because everyday experience seemed to offer overwhelming evidence to the contrary. When a torch is lit, the darkness disappears instantly, or so it appears, and when lightning splits the sky, the flash is seen immediately while the thunder arrives later, reinforcing the intuitive belief that light has no delay at all. To early observers, light did not seem to move, it simply appeared, filling space without effort or travel, and this intuition shaped philosophical thought for centuries. In a world without precise instruments, without fast clocks or long-distance measurements, there was no reason to suspect otherwise. Light seemed fundamentally different from sound, arrows, or thrown stones, which clearly took time to cross distances. Because light appeared to arrive the moment it was created, many assumed it must propagate infinitely fast, existing everywhere at once. Ancient thinkers debated the nature of light intensely, but their discussions focused more on what light was rather than how fast it moved. Some imagined it as a substance streaming from the eyes, others as something emitted by luminous objects, but speed was rarely questioned because it seemed irrelevant. One of the earliest figures to challenge this assumption was the Greek philosopher Empedocles, who proposed that light was something in motion, and therefore must require time to travel from its source to the observer. This was a radical idea for its era, suggesting that seeing was not instantaneous but delayed, even if imperceptibly so. However, Empedocles' view failed to gain lasting influence, largely because it conflicted with the authority of Aristotle, whose writings would dominate Western thought for nearly 2 millennia. Aristotle argued that light was not a moving entity at all, but a kind of instantaneous state change in the medium between object and observer, similar to how a room becomes illuminated when a lamp is uncovered. According to this view, light did not travel, it simply manifested. Because Aristotle's work formed the backbone of education and philosophy throughout much of Europe and the Mediterranean world, his conclusions were rarely challenged. Once his ideas were absorbed into religious and scholastic traditions, questioning them became not only intellectually difficult but culturally discouraged. As a result, the belief that light moved instantaneously hardened into accepted truth, passed down from generation to generation without experimental scrutiny. Even as civilizations advanced in architecture, navigation, and mathematics, the assumption remained untouched, largely because no one had the means to test it. Human perception simply was not sensitive enough to detect delays that might exist over everyday distances, and without clocks capable of measuring tiny fractions of a second, the question of light's speed remained invisible. The very success of light in illuminating the world reinforced the illusion of immediacy. Sight felt direct and immediate in a way that sound never did. As societies developed technologies like mirrors, lenses, and early optical instruments, attention turned toward the behavior of light in reflection and refraction, not its velocity. The absence of any noticeable delay became evidence in itself, creating a circular logic where invisibility was mistaken for non-existence. This long-standing assumption illustrates a recurring theme in science. When phenomena operate far beyond the limits of human perception, intuition becomes unreliable. The idea that light might take time to travel was not rejected because it was disproven, but because it seemed unnecessary. Only when thinkers began to question whether nature should be trusted to align with human experience did cracks appear in this certainty. The ancient world, for all its intellectual brilliance, lacked the experimental framework needed to challenge such deeply rooted assumptions. Philosophy could ask whether light was instantaneous, but without measurement, the question remained suspended between speculation and dogma. It would take a fundamental shift in how knowledge was pursued, moving away from authority and toward observation, before the speed of light could become a scientific problem rather than a philosophical curiosity. The belief in instantaneous light was not foolish. It was a reasonable conclusion drawn from limited evidence. But as history would reveal, the universe does not owe its behavior to human intuition, and the truth about light's motion lay hidden beyond the reach of unaided senses, waiting for a new way of thinking to bring it into focus. As European thought remained anchored to ancient authority, a different intellectual tradition was quietly laying groundwork that would later prove crucial, particularly in the Islamic world, where scholars approached light with a more experimental and analytical mindset. Rather than treating vision as a purely philosophical problem, they examined how light actually behaved, how it interacted with surfaces, and how it moved through space. One of the most influential figures in this tradition was Ibn al-Haytham, known in the West as Alhazen, whose early 11th century work on optics represented a dramatic break from classical assumptions. He argued that vision occurs not because the eyes emit something outward, but because light travels from external objects into the eyes, a concept that now seems obvious but was revolutionary at the time. Crucially, he also proposed that light does not propagate instantaneously, but moves through space at a finite rate and behaves differently depending on the medium it passes through. According to his observations, light slows when traveling through denser materials, bending and scattering in ways that could be measured and described mathematically. This insight alone placed him centuries ahead of his time, anticipating discoveries that would not be experimentally confirmed until the modern era. Yet despite the clarity of his reasoning, these ideas remained largely theoretical, constrained by the same limitation that had plagued earlier thinkers: the absence of tools capable of measuring extremely short intervals of time. Without precise clocks or methods to isolate light's travel over vast distances, even the most accurate conceptual model could not rise above informed speculation. A correct idea without experimental verification carries little authority in science, and so these insights, while brilliant, failed to overturn the dominant belief in instantaneous light. As knowledge later flowed from the Islamic world into Europe, many of these works were translated, studied, and absorbed, but their most radical implications were often overlooked or softened to fit existing frameworks. European scholars adopted optical principles related to lenses and vision, while leaving deeper questions about light's speed untouched. The scientific culture of the medieval period favoured synthesis over challenge, reconciliation over disruption, and this slowed the acceptance of ideas that threatened long-held assumptions. Still, something had changed beneath the surface. The notion that light might be a physical phenomenon subject to motion, delay, and variation had been planted. Over time, this seed would grow as thinkers began to prioritize observation over deference. The gradual rise of experimental science in the late Renaissance created conditions where such questions could no longer be ignored. Instruments improved, distances became measurable, and curiosity shifted from why the world should behave a certain way to how it actually does. Light, once thought too immediate to measure, became a legitimate subject of investigation. Scholars began to recognize that imperceptibility does not imply non-existence, and that nature often operates on scales far removed from human sensation. The challenge was no longer philosophical but practical. How could one detect a delay so small that it vanished within human reaction time? This question marked a turning point, transforming the speed of light from an abstract debate into an experimental problem waiting for a method. The intellectual bridge between medieval insight and modern physics was fragile but real, built on the recognition that light behaves differently in different materials, and that its interaction with matter reveals hidden properties of motion and structure. Though centuries would pass before these ideas could be fully tested, they established a critical precedent. Light was not magical or instantaneous by necessity, but governed by rules that could, in principle, be discovered. What remained was the development of techniques powerful enough to expose those rules, and the willingness to trust measurement over tradition when the results finally arrived. The first serious attempt to measure the speed of light did not come from vast observatories or elaborate machinery, but from an experiment so simple in concept that it bordered on the naive, yet it marked a crucial step forward because it treated light's velocity as something that could, in principle, be measured. In the early 17th century, Galileo Galilei, one of the founders of modern experimental science, proposed a method that relied on nothing more than distance, visibility, and human reaction. His idea was straightforward. Two observers would stand on separate hilltops at night, each holding a lantern that could be quickly uncovered and covered again. The first observer would uncover their lantern, and the moment the second observer saw the flash, they would uncover theirs in response. By measuring the time between the first signal and the return flash, Galileo hoped to determine how long light took to travel across the gap and back again. If light were truly instantaneous, there would be no measurable delay beyond human response time. If it were finite, even an incredibly small delay might reveal itself. Galileo carried out versions of this experiment at distances of less than a mile and found no detectable lag at all. Rather than concluding that light had infinite speed, he drew a more cautious and scientifically honest conclusion. If light does take time to travel, that time is far too small to measure using this method. What Galileo did not know, and could not have known given the technological limits of his era, was just how extreme the mismatch was between the scale of the phenomenon and the sensitivity of his tools. Light can cross a mile in roughly 5 millionths of a second, while human reaction time is measured in tenths of a second, a difference of tens of thousands of times. Even the slightest hesitation in uncovering a lantern would completely overwhelm the effect he was trying to observe. The experiment was doomed not because the idea was wrong, but because the available measuring instrument, the human nervous system, was hopelessly inadequate. Later scientists would recognize this as a classic example of scale blindness, where a phenomenon exists far outside the range of direct perception. Galileo's failure was therefore not a setback, but a diagnostic result, revealing that any successful measurement would require either vastly greater distances or a way to bypass human reaction entirely. His experiment was repeated decades later by scientific academies with identical results, reinforcing the conclusion that terrestrial distances were simply too small. Yet the importance of Galileo's attempt lies in what it represented, a decisive shift away from philosophical argument toward experimental inquiry. For the first time, the speed of light was treated not as a metaphysical question, but as a measurable physical quantity. Galileo demonstrated that absence of evidence is not evidence of absence, and that negative results still carry information. His work clarified the path forward by eliminating small-scale experiments as viable options, pointing instead toward the heavens. If light crossed a mile too quickly to measure, perhaps it could be measured across millions of miles. This realization quietly set the stage for a breakthrough that would come not from lamps and hilltops, but from the motion of planets and the ticking of celestial clocks. Galileo's lanterns failed, but they illuminated something far more important than a number. They showed that the universe operates on scales that demand new methods, and that understanding nature sometimes requires abandoning the familiar world entirely in favor of distances so vast that only astronomy can reveal the truth. The breakthrough that finally revealed light's finite speed did not emerge from an experiment designed for that purpose, but from careful astronomical observation combined with a willingness to question assumptions that others had overlooked. In the late 17th century, the Danish astronomer Ole Rømer was working in Paris, tasked with refining predictions of celestial events that were thought to be perfectly regular. His focus was Jupiter's moon Io, whose orbital motion caused it to disappear behind the planet at precise, predictable intervals. These eclipses were so reliable that they were used as natural clocks, valuable for navigation and for improving astronomical tables. Over time, however, Rømer noticed something unsettling. The observed timings did not always match the predictions. The discrepancies were not random errors or observational mistakes, but systematic shifts that followed a pattern. When Earth was moving toward Jupiter in its orbit around the Sun, Io's eclipses appeared to occur slightly earlier than expected. When Earth was moving away, they appeared later. The difference accumulated gradually, reaching several minutes over the course of a year. At first glance, this might have seemed like a flaw in the orbital model, but Rømer realized that the moon's motion itself was not changing. The only variable that correlated with the timing differences was the distance between Earth and Jupiter. This led him to a radical conclusion. The eclipses were happening exactly when they should, but the light-carrying news of those events took time to reach Earth, and that time depended on how far the light had to travel. When Earth was closer, the information arrived sooner. When Earth was farther away, it arrived later. In effect, astronomers were not seeing the events as they happened, but as they were delayed by the finite speed of light. This was a profound shift in perspective, transforming observation into a historical record rather than a real-time report. Rømer reasoned that if light were instantaneous, the timing of Io's eclipses would be unaffected by Earth's motion. The fact that they were not could only be explained if light required time to cross space. He went further, using the size of Earth's orbit as a baseline to estimate how long light took to travel across it. Though the exact dimensions of the solar system were not yet well known, Rømer calculated that light required roughly 22 minutes to cross the diameter of Earth's orbit. This was the first quantitative estimate of light speed in history. While the numerical value was significantly off by modern standards, the conceptual leap was flawless. Rømer did not merely suggest that light was finite, he demonstrated it through prediction. He announced that an upcoming eclipse of Io would occur noticeably later than existing tables indicated, based solely on the increased distance light would have to travel. When the predicted delay occurred exactly as he said, skepticism collapsed. The universe itself had confirmed his hypothesis. This moment marked a turning point, proving that light does not act instantaneously, but races across space at a measurable speed. It also revealed something deeper. Observation is inseparable from time delay. Every astronomical event is seen in the past, separated from the observer by the finite speed of information. What Rømer uncovered was not just a property of light, but a new understanding of perception itself. The sky was no longer a synchronized display but a layered archive of events, each arriving according to its distance. Though many contemporaries resisted the idea, preferring simpler explanations, the evidence was undeniable. A cosmic scale had succeeded where earthly experiments had failed, showing that to measure the fastest thing in nature, one must look beyond the limits of the human world and let the motion of planets reveal what our senses could not. Rømer's insight would have remained an intriguing hypothesis had it not been for the boldness with which he put his idea to the test, staking his reputation on a prediction that the heavens themselves would either confirm or refute. Rather than merely explaining past discrepancies, he publicly announced that the established tables for Jupiter's moon Io were wrong in a specific and measurable way. According to his calculations, an upcoming eclipse would occur significantly later than predicted, not because the moon's orbit had changed, but because Earth would be farther away at that point in its own journey around the Sun. This was an audacious move in an era when challenging accepted astronomical tables was risky and often unwelcome. If Rømer was mistaken, the error would be obvious to anyone watching the sky. When the critical date arrived, astronomers observed the eclipse exactly when Rømer had forecast, delayed by the precise amount he predicted. The result left little room for alternative explanations. The moon had not slowed down, the tables had not failed, light itself had taken longer to deliver the information. This confirmation transformed Rømer's proposal into the first successful measurement of light speed, even if the number itself lacked precision. His estimate was lower than the true value by a substantial margin, largely because the size of Earth's orbit was not yet accurately known. But this numerical error did not diminish the achievement. For the first time in history, light was shown to be finite, measurable, and governed by the same physical constraints as other natural phenomena. The implications were profound and unsettling. If light took time to travel, then the universe was not observed as it existed in the present moment, but as it existed in the past. Astronomers were not seeing Jupiter and its moons as they were, but as they had been minutes earlier, and the same logic extended outward indefinitely. Every star, every planet, every nebula was a delayed image, separated from the observer by the time light needed to cross space. Rømer's work quietly introduced the idea that distance is inseparable from time, long before anyone had language to describe space-time itself. Despite the strength of the evidence, acceptance was not immediate. Some astronomers attempted to attribute the delays to irregularities in Io's orbit or imperfections in observation, reluctant to abandon the notion of instantaneous light. The concept was simply too alien, too disruptive to established thinking. Yet the predictive success of Rømer's method made these objections increasingly untenable. His results were published, discussed, and debated across Europe, slowly reshaping scientific consensus. Over time, the idea that light travels at a finite speed became not just plausible, but unavoidable. Even those who questioned the exact value could not deny the underlying principle. What made this discovery especially remarkable was that it emerged without new instruments or controlled experiments, relying instead on patience, careful record-keeping, and a willingness to interpret discrepancies as clues rather than errors. Romer did not invent a device to measure light. He used the solar system itself as a laboratory, with Jupiter's moons serving as celestial clocks and Earth's orbit providing a changing baseline. This approach revealed a new way of doing science, one that embraced the vast scales of astronomy to answer questions unreachable on Earth. Although decades would pass before independent confirmation arrived, the conceptual foundation had been laid. Light was no longer an instantaneous messenger, but a traveller, bound by distance and delay. The universe had acquired depth not only in space but in time, and humanity had taken its first step toward understanding that the act of observation is always an encounter with the past. More than half a century after Romer's discovery, a completely different line of investigation provided independent confirmation that light does not arrive instantaneously, reinforcing the idea through a phenomenon that had nothing to do with planetary moons or eclipses. In the early 18th century, English astronomer James Bradley set out to measure stellar parallax, the subtle shift in a star's apparent position caused by Earth's motion around the Sun. Detecting this shift was considered one of the most important unsolved problems in astronomy, because it would offer direct proof that Earth truly orbits the Sun rather than remaining fixed at the center of the universe. Bradley constructed extremely precise instruments and began observing stars over long periods, expecting to see tiny back-and-forth motions that corresponded to Earth's changing vantage point. What he found instead was something unexpected. The stars did appear to shift position over the course of a year, but the pattern was wrong for parallax. The displacement was too large, occurred in the wrong direction, and followed a timing that did not match the predictions of orbital geometry. Rather than dismissing the result as an error, Bradley looked for an explanation that could account for the strange behavior. The breakthrough came through an everyday analogy. While traveling by boat, Bradley noticed that the apparent direction of falling rain changed depending on the motion of the vessel, even though the rain itself was falling straight down. To stay dry, one had to tilt an umbrella forward when moving into the rain, not because the rain was angled, but because motion altered how it was encountered. Bradley realized that starlight behaves the same way. Even if light from a distant star travels straight toward Earth, the motion of the observer causes the apparent direction of that light to shift. As Earth moves through space, the telescope must be tilted slightly in the direction of motion to capture the incoming light, producing a systematic displacement known as stellar aberration. This effect only makes sense if light takes time to travel. If light were instantaneous, Earth's motion would be irrelevant, and no aberration would occur. The magnitude of the shift depended on the ratio between Earth's orbital speed and the speed of light, allowing Bradley to calculate light's velocity using known values of Earth's motion. His result was remarkably close to the modern value, deviating by only a small percentage. What made this discovery especially powerful was that it relied on an entirely different principle from Romer's method. Romer measured delays in timing caused by changing distances, while Bradley measured angular shifts caused by observer motion. The agreement between the two approaches eliminated any lingering doubt. Light had a finite speed, and that speed could be measured consistently using independent phenomena. Stellar aberration also introduced a subtle but important insight. Observation is influenced not only by where you are, but by how fast you are moving. The universe does not present itself the same way to all observers, even when they are looking at the same object. Bradley did not fully grasp the deeper implications of this idea, but it foreshadowed concepts that would later become central to relativity. His work showed that motion alters perception in systematic, predictable ways, governed by the finite speed of light. Over time, stellar aberration became a standard tool in astronomy, further cementing the reality of light's travel time. With two independent confirmations separated by decades and based on entirely different observations, the notion of instantaneous light finally collapsed. What had once seemed obvious was now known to be false. Light was fast beyond imagination, but not infinitely fast. The universe had revealed yet another layer of complexity, demonstrating that even the act of seeing is shaped by motion, distance, and time, and that understanding nature requires looking beyond appearances to the hidden mechanisms beneath. Once astronomers had shown that light's speed was finite using the vast distances of space, the next challenge was to bring the measurement back down to Earth and determine whether this cosmic constant could be captured within the confines of a laboratory. This problem had defeated Galileo centuries earlier, not because the idea was flawed, but because the scale was wrong. Light simply moved too fast for short distances and human reflexes. By the mid-19th century, however, technology had advanced to the point where mechanical motion could be controlled with sufficient precision to serve as a clock far faster than any human reaction. In 1849, the French physicist Hippolyte Fizeau devised an ingenious experiment that finally succeeded in measuring the speed of light over a terrestrial distance. His setup was elegant in its simplicity, yet precise in execution. A bright light source was placed on a hill outside Paris, aimed toward a mirror positioned several miles away. Between the source and the mirror, Fizeau installed a rapidly rotating wheel with hundreds of evenly spaced teeth. When the wheel was stationary or turning slowly, light passed through a gap between the teeth, traveled to the distant mirror, reflected back, and returned through the same gap, reaching the observer. As the wheel's rotation speed increased, the timing changed. At a specific speed, the returning light was blocked by a tooth that had rotated into place during the light's round trip, causing the light to disappear. Increasing the speed slightly further allowed the returning beam to pass through the next gap instead. By carefully measuring the rotation speed at which these transitions occurred, Fizeau could determine how long it took for light to travel to the mirror and back. Knowing the distance and the mechanical timing of the wheel, he calculated light's velocity. Although his result was slightly higher than the modern value, the error was small enough to be attributed to uncertainties in distance measurement and mechanical limitations. What mattered was the achievement itself. For the first time, light's speed had been measured without relying on planets, stars, or cosmic distances. The fastest phenomenon in nature had been clocked using human-made machinery on Earth. This experiment marked a turning point, proving that the laws governing the cosmos also applied in the laboratory. Light was no longer an abstract astronomical curiosity. It was a measurable physical entity subject to experimental control. Fizeau's work also demonstrated the power of indirect measurement, where time too short to measure directly could be inferred through motion, rotation, and geometry. The success of this approach opened the door to further refinements, inspiring other physicists to seek even greater accuracy. It also symbolized a broader shift in science, where precision engineering became as important as theoretical insight. By replacing human reaction time with mechanical regularity, Fizeau overcame the very limitation that had stopped Galileo. His toothed wheel transformed motion into a clock fast enough to keep pace with light itself. This achievement bridged the gap between celestial observation and laboratory physics, showing that the same constant governed both the heavens and the Earth. Light's speed was no longer merely inferred, it was captured, quantified, and brought under experimental scrutiny, setting the stage for even more refined techniques that would push precision to unprecedented levels. Fizeau's success proved that light's speed could be measured on Earth, but it also revealed the limitations of mechanical systems and distances that were still modest by cosmic standards, motivating physicists to search for methods that offered greater precision and deeper insight into the nature of light itself. Among those who took up this challenge was Léon Foucault, a French physicist whose refinements would not only improve accuracy, but also resolve a long-standing theoretical dispute about what light actually is. Foucault replaced the toothed wheel with a rapidly rotating mirror, a design that allowed much finer control over timing and significantly reduced mechanical uncertainties. In his setup, a beam of light was reflected off a spinning mirror toward a distant fixed mirror and then sent back along the same path. Because the mirror rotated slightly during the light's round trip, the returning beam was deflected by a tiny but measurable angle. By precisely measuring this deflection and knowing the mirror's rotation speed, Foucault could calculate the time taken by light to travel the distance. This method proved to be far more accurate than earlier approaches, and by the early 1860s, Foucault obtained a value astonishingly close to the modern accepted speed of light. Yet his most important contribution was not merely numerical. Years earlier, he had used the same rotating mirror technique to compare the speed of light in air and in water, producing a result that settled a debate that had persisted since the time of Isaac Newton. Newton had argued that light consisted of tiny particles, and according to his theory, These particles should move faster in denser materials like water, pulled along by attractive forces within the medium. A competing wave theory, developed by others, predicted the opposite. Waves should slow down when passing through denser substances, much as sound behaves differently in air and solids. Foucault's experiment demonstrated conclusively that light travels more slowly in water than in air, delivering a decisive blow to Newton's particle model. This was a remarkable moment in the history of science, not because Newton had been careless, but because even the greatest minds can be wrong when evidence is incomplete. The results showed that light behaves fundamentally like a wave, governed by interactions with matter rather than simple ballistic motion. This finding reshaped optics and laid the groundwork for later theories that would merge wave and particle behavior into a deeper quantum framework. Foucault's work illustrated a powerful principle. Measuring how light slows down can reveal as much about its nature as measuring how fast it moves. The medium became a probe, exposing hidden structure in the interaction between light and matter. At the same time, the rotating mirror technique pushed experimental physics toward unprecedented precision, demonstrating that abstract constants could be pinned down with remarkable accuracy using carefully designed instruments. Light, once thought instantaneous and intangible, was now subject to the same rigorous scrutiny as any other physical phenomenon. These experiments also hinted at something more subtle, that the speed of light might not simply be a property of light alone, but a feature emerging from deeper laws governing space, matter, and energy. By the time Foucault completed his measurements, the question of whether light had a finite speed was long settled, but the meaning of that speed was becoming increasingly mysterious. Precision had replaced doubt, yet with it came new questions about why light behaved as it did and what deeper principles enforced its limits. The refinement of measurement had not closed the story. It had opened the door to an even more radical rethinking of reality that would soon follow. As measurements of light's speed grew increasingly precise, physicists began to confront a troubling inconsistency between experimental results and the theoretical picture they relied upon to explain how light traveled through space. By the late 19th century, it was widely accepted that light behaved as a wave, and by analogy with sound or water waves, waves required a medium through which to propagate. Sound needed air, ocean waves needed water, so it seemed natural to assume that light also needed a carrier, even in the apparent emptiness of space. This hypothetical substance came to be known as the luminiferous ether, an invisible, weightless medium thought to permeate all of space and provide the framework through which light waves could move. The ether was an extraordinary idea, designed to satisfy mutually contradictory requirements. It had to be rigid enough to support waves traveling at enormous speeds, yet so insubstantial that planets could pass through it without resistance. It had to fill all of space uniformly while remaining completely undetectable by any means other than its supposed effect on light. Despite these strange properties, the ether was not considered speculative. It was treated as a necessary component of reality. If the ether existed, and if Earth moved through it as it orbited the Sun, then Earth should experience something like an ether wind, analogous to the apparent wind felt when moving through air. Light traveling in the direction of this wind should behave differently from light traveling across or against it, producing small but measurable differences in speed depending on direction. These differences were expected to be tiny, but by this point, experimental techniques had become sensitive enough that such effects seemed within reach. The challenge was to design an experiment capable of detecting an almost imperceptible variation in light's behavior caused by Earth's motion through the ether. Enter Albert A. Michelson, a physicist obsessed with precision and measurement. Michelson believed that if the ether existed, its effects could not hide forever from sufficiently careful observation. He developed an instrument of unprecedented sensitivity called an interferometer, designed to compare the travel times of light along different paths with extreme accuracy. The logic was simple but powerful. A single beam of light would be split into two perpendicular paths, each reflecting off mirrors before recombining. If light traveled at different speeds depending on direction, the two beams would arrive out of phase, producing an interference pattern that would shift as the apparatus was rotated. By monitoring these shifts, one could directly detect Earth's motion through the ether. The expected signal was small but clear, and the experiment seemed almost guaranteed to succeed. Yet beneath this confidence lurked a deeper problem. Every previous attempt to detect the ether had failed, producing results that stubbornly refused to reveal any directional dependence in light speed. Still, physicists remained convinced that the ether must exist, and that the failures reflected experimental imperfections rather than a flawed assumption. Michelson's interferometer represented the culmination of decades of refinement, offering a final decisive test. If the ether was real, this instrument would find it. If not, physics would face a crisis. The stage was set for an experiment that would not merely measure light speed, but challenge the very foundation of how scientists understood waves, motion, and space itself. When Michelson joined forces with Edward Morley to carry out the ether experiment, expectations were high that decades of uncertainty would finally be resolved, and few doubted that the elusive medium would at last reveal itself. The apparatus they constructed was a triumph of experimental design, built to detect differences in light travel time far smaller than anything previously attempted. At its heart was the interferometer, mounted on a massive stone slab and floated on a pool of mercury to isolate it from vibrations and allow smooth rotation. A single beam of monochromatic light was split into two paths arranged at right angles, each traveling the same total distance before being recombined. If Earth were moving through the ether, one beam should encounter resistance from the ether wind, while the other moved across it, producing a tiny difference in travel time. When recombined, this difference would shift the interference fringes in a predictable way. Michelson and Morley carefully calculated the expected magnitude of this shift based on Earth's known orbital speed and the assumed properties of the ether. The predicted signal was small, but well within the sensitivity of their instrument. Over months of painstaking measurements, they rotated the apparatus through different orientations and repeated observations at different times of day and year, expecting the pattern to change as Earth's velocity through the ether varied. But the shift never appeared. No matter how the interferometer was oriented, no matter when the measurements were taken, the interference pattern remained essentially unchanged. The observed variation was a tiny fraction of what the ether theory demanded, so small that it could not plausibly be explained by experimental error. The result was profoundly unsettling. Michelson and Morley had not merely failed to detect the ether, they had found compelling evidence that it did not exist in the way everyone believed. Light appeared to travel at the same speed in all directions, regardless of Earth's motion. This outcome, often described as a null result, became one of the most famous in the history of science, not because nothing happened, but because what did not happen contradicted the deepest assumptions of 19th century physics. The ether, which had seemed indispensable, now appeared unnecessary, or at least undetectable. Physicists responded with a mix of confusion and ingenuity. Some proposed that the ether was somehow dragged along with Earth, eliminating relative motion. Others suggested that physical objects contracted in the direction of motion through the ether, exactly cancelling the expected effect. These explanations preserved the ether at the cost of introducing increasingly contrived mechanisms. Few were ready to abandon the ether entirely, because doing so meant confronting a far more radical possibility, that the laws of physics might not depend on any absolute background at all. Michelson himself regarded the result with ambivalence, recognizing its importance but uncertain of its interpretation. What was clear was that light behaved in a way no existing theory could fully explain. The experiment had revealed a deep inconsistency between measurement and expectation, a sign that something fundamental was missing. The universe had delivered a clear answer to a well-posed question, and that answer was deeply uncomfortable. The speed of light, it seemed, was not merely a property of waves moving through a medium, but something more intrinsic, something that refused to vary even when every classical argument insisted it should. The Michelson-Morley experiment did not solve the problem of light, it exposed it, clearing the stage for a revolutionary idea that would soon redefine space, time, and motion themselves. As the implications of the Michelson-Morley experiment slowly sank in, physicists found themselves in an unusual position. They could measure the speed of light with extraordinary accuracy, yet they no longer understood why that speed behaved the way it did. Over the following decades, experimental techniques continued to improve, producing values that agreed more closely with one another, but still left the deeper mystery unresolved. Eventually, the focus shifted from refining the number to recognizing what that number represented. By the late 20th century, the speed of light had proven to be not just another measured quantity, but a cornerstone of the physical world, appearing again and again in the fundamental equations governing electromagnetism, relativity, and energy. In 1983, the international scientific community took a decisive step that reflected this realization. Rather than continuing the endless pursuit of ever more precise measurements, scientists redefined the meter itself in terms of the speed of light. The value was fixed by definition, making the speed of light in vacuum an exact number with no experimental uncertainty. This was not an admission of defeat, but an acknowledgement of understanding. Length was no longer something used to determine light's speed. Instead, light's speed became the reference against which length was defined. This shift revealed a profound change in perspective. The speed of light was no longer treated as a contingent property of nature that needed continual verification, but as a fundamental constant woven into the structure of reality. By anchoring measurement systems to it, physicists acknowledge that this speed is as fixed and reliable as any concept in science can be. This decision also reflected a deeper insight gained through centuries of experimentation. The speed of light does not vary from place to place or time to time. It is the same in laboratories, in space, and across cosmic distances. In that sense, it resembles a rule rather than a measurement, a constraint that everything else must obey. Defining units in terms of such constants reduces ambiguity and increases precision, allowing science and technology to operate on a stable foundation. This redefinition also symbolized the end of an era in which light speed was something mysterious and contested. The debate over whether light was instantaneous, finite, or variable had been settled beyond doubt. What remained was the task of understanding its consequences. Fixing the speed of light by definition did not trivialize its importance, it elevated it. It recognized that this speed plays a role similar to the flow of time itself, setting a universal scale that underlies all physical processes. By making the meter dependent on the speed of light, scientists implicitly acknowledged that space and time are inseparable from the behavior of light. Measurement became an expression of fundamental structure rather than an arbitrary convention. This act closed the historical chapter that began with lanterns on hilltops and moons orbiting distant planets. The question of how fast light travels was no longer open. Instead, the real mystery had shifted. Why does the universe have such a speed at all? And what does its constancy imply about the nature of space, time, and causality? Those questions could not be answered by better instruments alone. They required a conceptual revolution, one that had already begun quietly at the start of the 20th century and would soon transform physics forever. At the moment, when physics seemed trapped between precise measurements and conceptual confusion, a radical shift emerged from an unexpected source, not from a major university or laboratory, but from a modest office where a young man reviewed patent applications by day and thought about the nature of reality by night. In 1905, Albert Einstein, then a relatively unknown clerk working in the Swiss Patent Office, published a series of papers that would later be recognized as one of the most extraordinary intellectual achievements in history. Without access to advanced laboratories, extensive academic networks, or experimental apparatus, Einstein relied almost entirely on thought experiments, mathematical reasoning, and an uncompromising commitment to logical consistency. Among these papers was one that addressed the growing crisis surrounding the speed of light. Einstein had been haunted by a question since his teenage years. What would it mean to chase a beam of light? If someone could move alongside light at the same speed, classical physics suggested that the light wave should appear frozen in space, oscillating but not advancing. Yet this image conflicted directly with the equations of electromagnetism, which allowed no such stationary light. According to those equations, light must always propagate at a fixed speed, regardless of the observer. This contradiction revealed a deeper problem, not with light itself, but with the assumptions underlying space and time. Rather than modifying Maxwell's equations, which were well supported by experiment, Einstein chose to question the framework in which motion was understood. In doing so, he proposed a theory that abandoned the notion of absolute space and absolute time, concepts that had dominated physics since Newton. Instead, he suggested that the laws of physics should look the same to all observers who are not accelerating, and that the speed of light should be the same for all such observers, regardless of their motion or the motion of the source. These ideas, simple to state yet revolutionary in consequence, formed the foundation of special relativity. Einstein did not introduce these principles to explain one isolated experiment. He presented them as fundamental truths about how the universe operates. By taking the constancy of light's speed seriously, he resolved the contradictions that had plagued 19th century physics, but only by accepting conclusions that defied common sense. Space and time could no longer be independent, universal backgrounds against which events unfolded. They became dynamic, observer-dependent quantities that adjusted themselves to preserve the cosmic speed limit. This shift transformed the speed of light from a puzzling measurement into a structural feature of reality. Einstein's insight was not merely technical, it was philosophical. He recognized that intuition shaped by slow speeds and everyday distances could not be trusted when confronting the deep structure of the universe. What mattered was not how things seemed, but how the equations demanded they behave. The consequences of this realization would soon ripple outward, reshaping every aspect of physics and revealing that the speed of light was not just fast, but fundamentally different from any other speed, acting as a bridge between space and time themselves. Einstein built his new understanding of the universe on two deceptively simple principles that, when taken together, shattered the familiar foundations of classical physics. The first was the principle of relativity, which states that the laws of physics are the same for all observers who are moving at constant velocities relative to one another. There is no preferred state of rest, no absolute frame against which motion can be measured. Whether you are standing still on Earth or traveling smoothly in a spacecraft, the fundamental rules governing nature do not change. This idea was not new, having its roots in the work of Galileo, but Einstein elevated it from a statement about mechanics to a universal principle applying to all of physics. The second principle was far more radical. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This assertion directly contradicted everyday intuition, which assumes that velocities simply add. If you throw a ball forward while riding on a moving train, someone standing on the platform sees the ball move faster than someone on the train. Classical reasoning would suggest that light should behave the same way, traveling faster when emitted from a moving source. Yet every experiment indicated otherwise. Einstein accepted this result not as an anomaly to be explained away, but as a fundamental fact. The consequence was unavoidable. If everyone measures the same speed of light, then time and space themselves must adjust to make this possible. Clocks cannot tick at the same rate for all observers, and distances cannot remain fixed. Instead, time dilates and lengths contract in precisely the way required to preserve the constancy of light speed. This was not a philosophical reinterpretation, but a mathematical necessity. Once the two postulates are accepted, the familiar rules for adding velocities break down, replaced by a new framework in which no combination of sublight speeds can ever exceed the cosmic limit. Motion ceases to be absolute, and simultaneity loses its universal meaning. Events that occur at the same time for one observer may not occur at the same time for another, depending on their relative motion. This was perhaps the most disturbing implication of all because it undermined the idea of a shared present moment extending across the universe. Einstein showed that there is no single objective now that everyone agrees on. Each observer carries their own version of time, shaped by their state of motion. These conclusions were not introduced as speculative ideas, but as unavoidable consequences of taking the speed of light seriously. Classical physics had assumed that time and space were fixed, rigid containers within which motion occurred. Einstein reversed this relationship, revealing that motion shapes time and space instead. The speed of light became the thread that tied these concepts together, enforcing a structure that the universe could not violate. What made this framework so powerful was its internal consistency. The bizarre effects it predicted were not arbitrary. They emerged naturally from the demand that the laws of physics look the same to all observers and that light speed remain constant. In embracing these principles, Einstein did not simplify the universe. He revealed its deeper order, one in which the strange behavior of time and space is not a flaw but a feature. ensuring that causality remains intact and that the cosmic speed limit is preserved across all frames of reference. One of the most immediate and experimentally testable consequences of Einstein's framework is the phenomenon known as time dilation, the unsettling realization that time itself does not flow at the same rate for all observers. According to special relativity, when an object moves relative to you, the passage of time for that object slows down compared to your own, not as an illusion or measurement artifact, but as a real, physical effect. A clock in motion genuinely ticks more slowly than a clock at rest. This idea clashes violently with intuition, because time feels absolute in everyday life, advancing at a steady, universal pace that everyone shares. Yet this sense of uniformity is a byproduct of our limited experience at low speeds. Einstein demonstrated that time is elastic, stretching and compressing in response to motion in precisely the way required to preserve the constancy of the speed of light. A simple thought experiment illustrates why this must be so. Imagine a clock that measures time by bouncing a pulse of light between two mirrors. Each round trip of the light marks one tick. If this clock is stationary relative to you, the light travels straight up and down, covering a fixed distance at a fixed speed, producing a regular rhythm. Now imagine the same clock moving sideways at high speed. From your perspective, the light no longer travels straight up and down. Instead, it follows a diagonal path, because the mirrors move sideways while the light is in transit. This diagonal path is longer than the vertical one, but the light must still travel at the same speed. A longer path at the same speed means more time between ticks. The moving clock runs slow. Crucially, this slowdown is not specific to light-based clocks. Any physical process that can mark time must be affected in exactly the same way, because if different clocks behave differently, the laws of physics would no longer be consistent across reference frames. Chemical reactions, biological processes, atomic vibrations, and radioactive decay all slow down together. Time itself is what changes. The amount of dilation depends on how fast the object is moving relative to the observer, becoming negligible at everyday speeds but increasingly dramatic as velocities approach the speed of light. At half the speed of light, the effect is small but measurable. At 90%, it becomes impossible to ignore. As the speed approaches the cosmic limit, the slowdown grows without bound, so that from the perspective of a stationary observer, a clock moving at nearly the speed of light appears to almost freeze. From the moving object's own perspective, however, nothing feels unusual. Its internal processes proceed normally, highlighting a key feature of relativity. Each observer experiences their own time as flowing naturally, even though others may disagree about its rate. This reciprocity does not lead to contradiction, because there is no absolute clock against which all others are judged. Time dilation is symmetrical for observers in uniform relative motion, each seeing the other's clock as running slow. What breaks this symmetry is acceleration, a distinction that becomes crucial in scenarios involving changing frames of reference. Time dilation is not a metaphor or a theoretical curiosity. It has been confirmed countless times through precise experiments. High-speed particles created in Earth's atmosphere survive far longer than their normal lifetimes because their internal clocks run slow relative to ours. Atomic clocks flown on aircraft return showing measurable differences compared to clocks left on the ground. Satellites must account for time dilation to maintain accurate navigation systems. In every case, the predictions of relativity match reality with astonishing precision. The universe does not enforce a single universal tempo. Instead, it allows time to adapt, ensuring that the speed of light remains invariant for all observers. This revelation fundamentally alters what it means to measure duration, revealing that time is not a backdrop against which events unfold, but a dynamic participant shaped by motion itself. Alongside the slowing of time, Einstein's theory predicts another equally counterintuitive effect. Objects in motion become shorter along the direction in which they travel, a phenomenon known as length contraction. Like time dilation, this is not an optical illusion caused by perspective or signal delay, but a genuine physical change in measured length. An object moving relative to an observer occupies less space in the direction of its motion than it does when measured at rest. This contraction arises from the same underlying requirement that the speed of light remain constant for all observers. If time stretches for moving objects, space must compress in a complementary way to preserve the structure of physical laws. The amount of contraction depends on speed, becoming noticeable only as velocities approach a significant fraction of light speed. At everyday speeds, the effect is so tiny that it escapes detection entirely, reinforcing the illusion of rigid, unchanging space. But at relativistic speeds, contraction becomes dramatic. A spacecraft traveling at 90% of light speed would appear less than half its rest length to a stationary observer. Push closer to the cosmic limit, and distances shrink towards zero. This effect has profound implications for how different observers describe the same situation. From the perspective of the moving object, nothing appears compressed. It is the external world that seems altered instead. This symmetry is essential to relativity, ensuring that no frame of reference is privileged. The strangeness deepens when length contraction is combined with the relativity of simultaneity, the realization that different observers do not agree on which events occur at the same time. Measuring the length of a moving object requires determining the positions of its front and back simultaneously. But simultaneity itself depends on the observer's state of motion. Two observers moving relative to one another will disagree about whether those position measurements are made at the same moment. As a result, they can legitimately measure different lengths for the same object without contradiction. This interplay leads to famous thought experiments that expose how deeply our intuitions fail at high speeds. Consider an object longer than a container at rest, such as a ladder that does not fit inside a barn. If the ladder is carried at a speed close to light, a stationary observer can find a moment when the ladder fits entirely inside the barn because it is length contracted. From the perspective of the person carrying the ladder, however, the barn is the object that is contracted and the ladder never fits. Both descriptions are correct within their own frames of reference because they disagree about which events happen simultaneously. There is no single objective answer to the question of whether the ladder fits. Reality accommodates both views by abandoning the notion of universal simultaneity. This idea strikes at the heart of our everyday understanding of time. We instinctively believe that events across space share a common present, that now is a universal slice through the universe. Relativity reveals that this belief is unfounded. Events that are simultaneous for one observer may occur in a different order for another observer moving relative to the first. Einstein illustrated this with a thought experiment involving lightning striking both ends of a moving train. An observer standing on the ground sees the strikes occur at the same time, while an observer on the train sees one strike before the other. Neither observer is wrong. The disagreement does not arise from faulty measurement, but from the structure of spacetime itself. This relativity of simultaneity ensures consistency between time dilation and length contraction, preventing paradoxes and preserving the speed of light as an invariant limit. It also forces a radical re-evaluation of what it means for events to occur at the same time. The universe does not provide a single timeline shared by all observers. Instead, each observer carries their own slice of space-time shaped by motion. Length contraction, time dilation, and the relativity of simultaneity are not separate effects, but interconnected aspects of a deeper reality in which space and time are inseparable and responsive, bending as needed to uphold the fundamental rules of nature. Perhaps the most famous and emotionally striking illustration of relativistic time is the scenario known as the twin paradox, which brings the abstract consequences of time dilation into the realm of human experience. Imagine two identical twins who begin life side by side on Earth. One remains on the planet, while the other boards a spacecraft capable of traveling at speeds close to that of light and journeys to a distant star before turning around and returning home. From the perspective of the twin who stays on Earth, the situation seems straightforward. The traveling twin departs, moves at an extreme speed for many years, reverses direction, and eventually comes back. Because the spacecraft was moving rapidly for most of the trip, its onboard clocks ran slow, and when the twins reunite, the traveler has aged far less. This conclusion follows directly from time dilation and is uncontroversial from Earth's frame of reference. The paradox arises when one tries to reverse the perspective. During most of the journey, the traveling twin could claim to be at rest, watching Earth move away and then return. From that viewpoint, Shouldn't the Earthbound twin be the one who ages less? Relativity insists that all uniform motion is relative, so at first glance the situation appears symmetric. The resolution lies in recognizing that the symmetry is only apparent, not real. The traveling twin does not remain in a single inertial frame. To leave Earth, they must accelerate. To turn around, they must accelerate again. To come to rest upon return, they accelerate once more. The twin on Earth, by contrast, remains in essentially the same inertial frame throughout the entire experiment. Acceleration breaks the symmetry, distinguishing the experiences of the two twins in a fundamental way. While special relativity deals primarily with constant velocities, it still allows acceleration to play a crucial role in determining how different frames connect. When the traveling twin changes direction, their definition of simultaneity shifts abruptly. Events on Earth that were considered simultaneous before the turnaround are no longer simultaneous afterward. This jump in simultaneity accounts for the age difference without contradiction. The result is not a trick of perception, but a real difference in elapsed time. The traveling twin's heart has beaten fewer times, their cells have undergone fewer divisions, and their biological processes have unfolded more slowly relative to the twin who stayed behind. This outcome has been confirmed experimentally in multiple ways. Atomic clocks flown on aircraft and satellites return, showing precisely the differences predicted by relativity. Particles accelerated to high speeds in laboratories live longer than they would at rest, not because they resist decay, but because time itself runs more slowly for them. The twin paradox is therefore not a paradox at all, but a vivid demonstration that time is not universal. It is personal, shaped by motion and history. What makes this realization so unsettling is that it contradicts a deeply held intuition, that aging is absolute and unavoidable, proceeding at the same rate for everyone. Relativity reveals that this intuition is false. Time is not a single river carrying all beings forward together. It is a landscape through which different paths can be taken, resulting in different amounts of experience duration between the same two events. The twins begin together and end together, yet the amount of time they have lived through is not the same. This is not science fiction or philosophical speculation. It is a direct consequence of experimentally verified laws. The twin paradox forces us to confront the reality that time is not something that simply happens to us, but something that depends on how we move through the universe. While thought experiments like the twin paradox make relativity vivid, the true power of Einstein's ideas lies in how relentlessly they have been confirmed by real experiments across vastly different scales, from subatomic particles to global technology. One of the most striking confirmations comes from unstable particles created high in Earth's atmosphere. When cosmic rays strike atmospheric atoms, they produce muons, particles that exist for only a tiny fraction of a second before decaying. At rest, a muon survives for just over 2 microseconds, far too short to allow it to travel the many kilometers from the upper atmosphere to Earth's surface. Yet detectors on the ground record large numbers of muons arriving intact. The explanation is not mysterious once relativity is taken seriously. These particles move at speeds extremely close to the speed of light, causing time in their reference frame to pass more slowly relative to ours. From our perspective, their internal clocks run slow, allowing them to survive long enough to reach the ground. From the muon's own perspective, nothing unusual happens to their lifetime. Instead, the distance they must cross is shortened due to length contraction. Two completely different explanations, each valid in its own frame, converge on the same observable result. This mutual consistency is one of relativity's greatest strengths. Laboratory experiments have pushed this confirmation even further. In particle accelerators, muons and other short-lived particles are forced into circular paths at enormous speeds, experiencing accelerations far greater than anything encountered in everyday life. Despite these extreme conditions, their decay rates match the predictions of relativistic time dilation with remarkable precision. Acceleration itself does not alter the flow of time. Velocity does. Beyond particle physics, relativity reveals itself in technologies people rely on every day without noticing. Global positioning systems operate by comparing the timing of signals from satellites orbiting Earth. These satellites carry atomic clocks that tick with extraordinary accuracy, but their motion and position in Earth's gravitational field cause their clocks to run at different rates than clocks on the ground. Special relativity predicts that their high orbital speed makes them run slow, while general relativity predicts that weaker gravity at altitude makes them run fast. The combined effect is a net difference of tens of microseconds per day. If these relativistic corrections were ignored, GPS errors would accumulate rapidly, rendering navigation useless within minutes. Engineers do not treat relativity as a theoretical curiosity. They build it directly into system design. Every successful GPS calculation is an implicit verification of Einstein's equations. Even early experiments confirmed relativity's predictions with astonishing accuracy. Atomic clocks flown around the world on commercial aircraft return showing precisely the time shifts predicted by theory. Towers, laboratories, and satellites have all been used to demonstrate that clocks at different heights and velocities tick at different rates. In each case, the results agree with relativistic predictions to levels far beyond experimental uncertainty. When apparent contradictions arise, as they occasionally do, careful investigation consistently reveals mundane causes, such as timing errors or faulty equipment, not violations of relativity. Over more than a century of testing, no experiment has ever conclusively contradicted Einstein's framework. This extraordinary track record is why relativity is not considered provisional in the way many theories are. It has become a foundational part of modern physics, shaping how we understand energy, matter, gravity, and the large-scale structure of the universe. The effects may be small at human speeds and distances, but they are not optional. They are woven into reality itself, revealing that time and space respond precisely and predictably to motion and gravity. The universe does not merely allow relativity, it enforces it, again and again wherever we look. One of the most profound consequences of the speed of light being a fundamental constant is that it establishes an absolute limit on how fast anything with mass can move, a boundary that cannot be crossed no matter how advanced technology becomes. As an object accelerates, its energy increases, but in relativistic physics, energy and inertia are inseparably linked. The faster an object moves, the more resistant it becomes to further acceleration, as though its mass is effectively increasing. At low speeds, this effect is negligible, which is why everyday motion appears to follow simple rules. But as velocity approaches the speed of light, the energy required to gain even a tiny additional increase in speed grows dramatically. Each increment demands more energy than the last, until the requirement diverges toward infinity. Reaching the speed of light would require an infinite amount of energy, an amount that cannot exist in the physical universe. This is not a technological limitation, but a structural feature of space-time itself. The speed of light is not merely very hard to reach, it is unreachable for any object that has mass. This explains why particles like electrons, protons, and even entire spacecraft can approach light speed but never attain it. In contrast, particles with no mass, such as photons, are compelled to travel at exactly the speed of light. They have no choice. If they moved slower, they would possess zero energy and cease to exist. Light does not travel fast by coincidence. It travels at the only speed allowed by the laws governing massless entities. This distinction between massive and massless particles reveals why the speed of light is so deeply embedded in the structure of reality. It is the dividing line between what can slow down and what cannot, between objects that experience time and those that do not. For a photon, no time passes between emission and absorption, no matter how far it travels from an external perspective. The journey across billions of light years is, in its own frame, instantaneous. This concept defies intuition, but follows directly from the mathematics of relativity. The cosmic speed limit also reshapes how velocities combine. In everyday life, speeds add straightforwardly, but near light speed, this rule fails. Even if two objects move toward each other at extreme speeds, their relative velocity never exceeds the speed of light. The universe enforces this limit relentlessly, ensuring that no observer ever measures anything moving faster than light. This restriction preserves causality, the fundamental ordering of cause and effect. If faster than light motion were possible, effects could precede causes in certain frames of reference, leading to logical contradictions where events influence their own past. Relativity prevents this by making the speed of light the maximum speed at which information and influence can propagate. It is not just a speed limit on motion, but a speed limit on causation itself. Every signal, every interaction, every chain of cause and effect is bounded by this constraint. Attempts to imagine ways around it have produced intriguing ideas, from hypothetical particles to exotic space-time geometries, but each runs into severe problems. Faster-than-light communication would allow messages to arrive before they were sent, shattering the consistency of reality. Most physicists therefore conclude that the universe is constructed to forbid such violations, not as a matter of convenience, but as a requirement for logical coherence. The speed of light acts as a safeguard, preserving the order of events across space-time. It defines what can influence what can be known, and what must remain causally disconnected. This realization transforms the speed of light from a mere physical constant into a guardian of reality structure, ensuring that the universe remains intelligible, consistent, and free from paradox. The consequences of the speed of light extend far beyond physics laboratories and equations, shaping our place in the cosmos and forcing us to confront the limits of connection, knowledge, and even meaning in a universe of staggering scale. Because light travels at a finite speed, distance is inseparable from time, and looking outward into space is also looking backward into history. The light from the sun takes minutes to reach Earth, meaning we never see it as it is, only as it was moments ago. Light from distant stars and galaxies may have been traveling for thousands, millions, or billions of years before reaching us, carrying information from eras long gone. This turns every telescope into a time machine, allowing us to reconstruct the universe's past while denying us access to its present. Beyond a certain distance, this limitation becomes absolute. The universe is approximately 13.8 billion years old, yet the observable cosmos spans far more than that in light years, because space itself has been expanding while light was in transit. There are regions of the universe whose light will never reach us, not because it is too slow, but because space between us is growing faster than light can cross it. Those regions exist forever beyond our horizon, causally disconnected, unreachable by any signal or journey. Even within our own galaxy, the speed of light imposes profound isolation. Stars are separated by distances so immense that communication would take years or centuries, and travel within a human lifetime becomes effectively impossible. Any civilization that might exist elsewhere in the Milky Way would be confined to its own stellar neighborhood, cut off not by hostility or intention, but by the structure of space-time itself. This reality reframes questions about exploration and contact. The silence of the cosmos may not imply emptiness, but separation enforced by an unyielding speed limit. On a philosophical level, the speed of light challenges our most basic assumptions about time. If simultaneity is relative and no universal present exists, then the familiar flow of past, present, and future becomes suspect. Some interpretations of relativity suggest a block universe in which all events exist equally, with time resembling a landscape rather than a moving river. In this view, the passage of time is not an objective feature of reality, but a feature of consciousness, a way minds experience their journey through space-time. Whether this interpretation is correct remains debated, but it arises directly from the finite speed of light and the structure it imposes on causality. The speed of light also raises unanswered questions. Why does this constant have the value it does? Why not faster or slower? Physics currently offers no deeper explanation. The value appears fundamental, shaping chemistry, stars, and life itself. Change it significantly, and the universe would be unrecognizable, perhaps incapable of supporting complex structures at all. The speed of light may therefore be woven not just into physical law, but into the conditions that allow observers to exist. In this sense, it connects the cosmos to consciousness, linking abstract constants to lived experience. The journey to understand this speed has spanned centuries, from ancient speculation to astronomical insight, from failed experiments to revolutionary theory. What began as a question about how fast light travels ended as a revelation about what kind of universe we inhabit. The speed of light is not merely a limitation, it is a guide, revealing that reality is deeper, stranger, and more subtle than intuition suggests. It teaches us that time bends, space adapts, and causality has boundaries. And in doing so, it offers a humbling perspective. We are small, bound by cosmic limits, yet capable of understanding them. That understanding, hard-won and incomplete, is one of humanity's greatest achievements, a testament to our ability to look beyond appearances and grasp the hidden structure of the universe we call home.